Let's look into proximal splitting methods for L1 optimization. Here we consider the L1 optimization where phi, matrix phi, and vector y are given. M is strictly less than n, and hence the matrix phi is a fat matrix. We assume that phi has full row rank, that is, rank phi is m. Let's rewrite the optimization program using the indicator function. Define the constraint set C, a hyperplane in Rn defined by phi x is y. Then introduce the indicator function on the set C. The L1 optimization program is then equivalently rewritten as an unconstrained optimization like this. Now we have unconstrained optimization. We note that the cost function of the L1 norm plus the indicator function is proper, closed, and convex function, but not proximable. That is, we cannot obtain a closed form representation of the proximal operator for this function. So the proximal algorithm cannot be directly applied. However, we observed that both function f1 and f2 are proximable. Then we split the cost function as f is equal to f1 plus f2. Let's consider a general optimization problem of this, where f1 and f2 are proper, closed, and convex functions. We assume here that f1 and f2 are proximable. Then the well-known Douglas-Rachford splitting algorithm is given by this. This is an iterative algorithm that applies each proximal operators prox gamma f1 and prox gamma f2 separately. Now let's go back to our problem. We had the cost function, the sum of L1 norm and the indicator function. Now f1 is the L1 norm and f2 is the indicator function, and they are proximable. In fact, the proximal operators are given by soft thresholding operator for f1 and the projection operator onto a hyperplane C, which is given by this. Now we have got the algorithm. This is the Douglas-Rachford splitting algorithm for our L1 optimization. This algorithm is very simple. Douglas-Rachford algorithm only requires simple continuous mapping of the soft thresholding function S gamma and linear computation of matrix vector multiplication and vector summation. This is much faster and easier to implement than the standard interior point method. The standard interior point method requires to solve linear equations at each step. Instead, we don't need to such a heavy process in the splitting algorithm here. We then study another splitting method called proximal gradient method for L1 regularization. We here consider the L1 regularization or LASSO described by this. The cost function is the sum of two convex functions f1 and f2 defined by these. since F1 and F2 are both proximable, we can directly apply Douglas-Rachford splitting algorithm for this problem. However, we see F1 is also differentiable. By using this property, we obtain a yet faster algorithm for this type of optimization problem. Consider a general optimization problem described as this, where F1 is differentiable and convex, satisfying domain F1 is Rn. F2 is a proper closed and convex function as usual. Then the proximal gradient algorithm is given by this, where this is the gradient of F1. Let's look into this algorithm precisely. In the proximal gradient algorithm, we denote this function by phi xk. The function phi x is rewritten as this. Here we denote this by f1 tilde zx. The function f1 tilde zx is a linear approximation of f1z around the point x, as shown in this picture. The iteration becomes xk plus 1 is prox gamma f tilde xk, where f tilde x is f1 tilde zx plus f2z. This is a proximal algorithm for finding the minimizer of f tilde, which is an approximation of original f by using linearized f1. This is a theorem for convergence of the proximal gradient algorithm. Assume that the gradient nabla f1 is Lipschitz continuous over Rn with Lipschitz constant L. Assume also that the step size gamma satisfies this inequality. Then the sequence xk generated by the proximal gradient algorithm converges to an optimal solution x asterisk at the rate of O 1 over k. Note that the gradient nabla f1 is Lipschitz continuous over Rn with Lipschitz constant L if this inequality holds for any xy in Rn. Now let's apply the proximal gradient algorithm to our L1 regularization or LASSO. The problem is this. In this problem, the cost function is the sum of two convex functions f1 and f2, where f1 and f2 are defined by this. With the gradient of f1 is given by this, and the proximal operator of f2 is the soft thresholding function. Then we have the proximal gradient algorithm, also known as ISTA, iterative shrinkage thresholding algorithm. This is also a very simple algorithm and very easy to implement. Let's consider the convergence of our algorithm, ISTA. The gradient is given by this. Then Lipschitz constant L of nabla f1 is obtained as follows. We have this inequality where lambda max phi transpose phi is the largest eigenvalue of phi transpose phi. Therefore, we have L is equal to lambda max phi transpose phi, which is equal to sigma max phi squared, equal to the squared norm of matrix phi, where sigma max phi is the largest singular value of phi, and this is a matrix norm. From the theorem, a sufficient condition for convergence is given by this inequality. Also, from the theorem, the convergence rate is O 1 over k. Then we can accelerate the algorithm of ISTA, which is called FISTA, namely first ISTA. The convergence rate is O 1 over k squared. This is the algorithm. This is still simple and easy to implement, but much faster than ISTA. Finally, let's discuss generalized LASSO and ADMM. Let's consider a generalized regularization problem of this form, where psi is a matrix. We call this the generalized LASSO. If psi is the identity matrix, then this is LASSO. Note that the L1 norm of psi x is not proximable in general. That is, no closed form expression for its proximal operator exists. So we need yet another algorithm to solve this type of problem. Let us consider a general optimization problem described by this, where f1 and f2 are proper closed and convex functions, and psi is a matrix. For this problem, an algorithm called alternating direction method of multipliers, ADMM for short, is available. The algorithm is this. We here discuss the convergence of ADMM. Assume that f1 and f2 are proper closed and convex functions. Assume also that the Lagrangian Lxz lambda, defined by this, has a saddle point. That is, there exists x asterisk, z asterisk, and lambda asterisk such that this inequality holds for any x, z, and lambda. Then the residual Rk is equal to psi x minus zx goes to 0 as k goes to infinity. Also, the objective value f1 xk plus f2 zk converges to f asterisk, the infimum of f1 x plus f2 z as k goes to infinity. If psi transpose psi is invertible, then the sequence xk zk converges to an optimizer. Now let's get back to the generalized lasso given by this. The first update in ADMM is given by this. The proximal operator in the second update is the soft thresholding operator. Finally, we obtain the ADMM algorithm for generalized lasso. In this algorithm, the inverse matrix of this is computed offline. Moreover, if the matrix phi transpose phi plus gamma inverse psi transpose psi is a tridiagonal matrix, the linear equation of this with unknown x can be solved in order n. That is, the first update here can be computed very fast. Also, The second and third updates are also very easy. This is the ADMM algorithm. Now, let's consider a real application of generalized LASSO, namely image denoising. We have an original image of a cat and the noisy image here. The purpose is to remove noise from this image. We also need to preserve edges at the same time, since applying a low-pass filter does not work very well in this case. Let matrix Y be a noisy image. From matrix Y, we pull out each column vector, say Y, and solve the following optimization problem by one. Here, the first term, the L2 norm of x minus y, shows proximity to the data. And the sum is the total variation to preserve edges. Lambda is a positive weight. This is called total variation denoising. Define phi to be identity and psi is this matrix. Then the optimization problem becomes generalized LASSO described by this. Therefore, we can use ADMM. In this application of image denoising, the weight lambda should be carefully chosen. When we choose lambda to be 50, the restored image is obtained as this. The noise is a bit removed. If lambda is 100, we obtain a better image. But if lambda is 200, the image becomes worse compared with the previous one. This is the previous one, and this is the image when lambda is taken to be 200. Now we summarize this section. In convex optimization, a local minimum is a global minimum. L1 optimization problems appeared in this course are convex optimization. Proximal operators are used to derive fast algorithms for convex optimization with non-differentiable L1 norm and constraints.